Well, welcome everybody to this COVID-19 world that we live in today. Instead of being in front of you, we decided we're going to have to do this via PowerPoint and video stream. Hopefully it works out well, but I'm making actually no promises at this point. Today we're going to be talking about a project that was done for the city of Largo in Florida. They had some issues during significant wet weather events where they experienced excessive sanitary sewer overflows at multiple locations. As we go through the agenda, the things that we're looking at on the project is to identify the I&I, where is it coming from, what is the capacity of the system, and is the capacity during wet weather the only limitation to conveying the flow. We'll also be looking at the actual abatement alternatives and then completing the R&R planning portion of the project, as well as the complete design and capacity improvements. This project involved full-blown SSES, sanitary sewer evaluations, system capacity evaluation using hydraulic modeling, and the design and construction was very interesting as we utilized an approach that was more like a find and fix. As we identified the problems within the system during the SSES activities, the city and its contractors were available to actually remedy the situations while the flow monitoring was still going on. So we had a pre-flow monitoring condition or pre-flow monitoring SSO condition. We analyzed the wet weather events in real time with flow meters, and then we were able to look at the abatement issues or effects that we had on the fly. So as we got to the end and we got into some hardcore design and construction, we also utilized on-call contractors to do cured in place lining for mains, lateral lining, as well as open cut construction and replacement due to hydraulics. So when we look at the project, this was part of a $38 million program that the city of Largo undertook as part of their wet weather preparations. They upgraded a bunch of their lift stations and master lift stations to handle the flow to get it to the plants, as they originally had issues that would be one lift station pumping to another lift station, pumping to another lift station, and the problem just followed wherever the pumping was going. So the first part of the project was flow monitoring, followed by the dry weather hydraulic modeling, manhole inspections, smoke testing, night flow isolations, and CCTV inspections. We also did a lot of dye water flooding, dye water tracing as part of that stormwater inflow initiative. So when we look at the project areas, it was pretty much scattered all over the city of Largo. We did have lift station 12, 39, and 120, which are in close proximities to each other, whereas lift station 20 and lift station 16 were further apart. These are where they had chronic overflows and they were getting significant fines from DEP in Florida. So when we look at the project structure, flow monitoring, modeling, SSES, you can follow this flow chart pretty quickly and find out exactly where it was. When you see that APA contractors, those are our annual services contractors that were already in place and working for the city of Largo. I'm going to jump into the flow monitoring now. For flow monitoring, we used both open channels. Well, it was all open channel style flow monitoring for the initial phase of the project. Now we're also doing some side pressure flow monitoring as part of their permanent situation. But we used PSAs, which are submerged technology. We also used some Doppler velocity systems. And then we also looked at using a parameter for groundwater monitoring using divers, borrowed divers that were telemetry based, as well as our rainfall gauging. So as we go through this project, you'll see as we identify the I&I volumes in each lift station service area, we utilized 18 temporary flow meters, 10 rain gauges, 4 groundwater gauges, and the groundwater gauges and the flow meters in some cases remain there today. They were set into a permanent application. So everything we utilized in the field was remote telemetry units, so we were looking at the data at midnight, typically downloading once a day for all the information. When we lined up our groundwater and our rainfall and our flow, it was very interesting. So this is a hydrograph from the lift station 12, flow meter number 1 in that basin. And if you look at the data on this is October 23rd and 24th. During this period of time, we had about 2.29 inches of rainfall during that period. And you can see the spike in flow. And as you follow this across for 24 hours from 1400 back over to 1400, you'll see that the flows never normalized. as the blue line is identifying your average daily dry weather flow. The red line is identifying the wet weather flow that was measured during the event. So we have an average base volume of 792. We have a meter upstream from this site. So when we subtract that flow out, we get an isolated volume of 683,000 gallons per day. We look at our wet weather flow, 1.6. Again, we isolate that out using the wet weather flow from the upstream meter, subtracting that out. Our isolated flow becomes 1.4 million gallons. When we look at that rainfall-induced volume, that rainfall-dependent I&I, we come up with 723,000 gallons based on a 2.29-inch rainfall event. And now you start to see what the problem is. So immediately we went to smoke testing in all of the basins. We did comprehensive smoke testing. We did comprehensive manhole inspections, comprehensive CCTV inspections, comprehensive everything. We went into every single basin and identified it. The process that we utilized to do the smoke testing was all a cloud-based solution. So our field crews were going through the basins as they were smoke testing with Samsung tablets that were Bluetooth over to a Trimble R1 GPS receiver, and as such they could see themselves walking on the screen. And as they identified defects, they would take a photograph. The photograph would then drop an XY coordinate value for each of the defects that was encountered. So now when we wanted to print out our sheets, which are our smoke testing defect sheets, Esri's collector program allowed us to write an application where we could just go ahead and print every single defect with the address of the defect, with images of the defect, over to an 11 by 17 sheet. These sheets were then given to the client, and their staff went out to the field and rectified a lot of the inflow sources that were identified. So then we went into the manhole inspections, and the process for the manhole inspections was pretty simple. Again, we utilized a cloud-based solution, but at the front end of the project, we actually front-loaded the inspection forms with the city's GIS data. So all that existing attribute data was on the forms as we went to the field. So as they got to the field with an R1 receiver and they pointed at the structure that they were at on the map, the inspection form would automatically come up. Most of the attribution was already filled out on the form, and they would check that attribution to make sure that it was correct. So when we went to the field, we were using Esri's Survey 123. We transferred that data back over into Collector so that we could utilize it to develop our inspection logs. When a structure received a grade of when I say grade, an MACP grade, NASCO's PACP, MACP, LACP program was used as a protocol for collecting the data on the project. Anything with a 3, 4, or 5 required that we utilized a different inspection for the second pass. And in this case, we used EnviroSite's Clever Scan digital side scanning camera system to document what the structure's levels were. So as the camera is lowered, and you can see from the photo there that it sits on top of the manhole, it has a camera on the bottom, it has 4 cameras on the sides, and when it's lowered down into the structure, it automatically records everything that it sees. So this is a manhole out at the wastewater treatment plant, and one of the things that we were looking at when we did the topside inspection on this was it appeared there was active groundwater infiltration coming into the structure. So we brought the Clever Scan out, and we wanted to find out where it was actually coming from. From the ground surface, it looked like it was coming from a wall, but we didn't know exactly where. When we got into the inspection, if you look at the photo in the middle, the second photo, you can see that the water starts to fragment instead of having the flow running, and that's basically from the grit chamber. You can see directly below that there's active infiltration coming down the wall of the manhole. In this case, you can see that it's actually a patch. There was a 24-inch pipe there that someone put a fiberglass patch on that they didn't do a very good job, and it wasn't sealed appropriately. So then as we go through these observations, we document everything on every single structure and identify, and you can see the map on the side right there that identifies what defects were recorded in each one of the inspections. So if we take a blow up of that inspection form, we are documenting whether or not the defects that were recorded were a 1, 2, 3, 4, 5, 6, whatever. There's 15 different cases where a defect could trigger a rehabilitation process. So all of the structures went through this protocol. We also prioritized the rehabilitation. You can see on the third column over, rehab priority, and then comments associated with that rehab authority. So as we look over at our manhole rehabilitation actions, these are the 14 things that we did as part of our rehabilitation plan for each structure. All of this information was conveyed back over to the contractor who's doing the manhole rehabilitation on a map that had the spreadsheet on the map that identified what structure got what type of rehabilitation action. The cost estimates were real easy to put into it as well. We just used the legacy costing data that the city had as part of their contract, so we could generate what that cost was to do each structure rehab. We also went on to the nightfall isolation work, and that's where we were looking at the structures and the pipe sections in the middle of the night between 11 p.m. and 6 a.m. that had active flow. So when we found active flow within the pipe, we were documenting based on gallons per day, per inch diameter mile of pipe as to what that excessive value could be. For the project, we used 2,500 gallons per inch diameter mile as our cutoff for it being excessive, what is considered excessive infiltration. The next phase of the project involved CCTV inspections. And this is an image from Washington, D.C., from Arlington National Cemetery, where we were doing a bunch of stormwater inspections. But it shows very good, in good light, the actual systems that we use. We used what is referred to as a duct camera, a digital universal camera for the inspections. Again, this is all digital. It allowed us to very quickly go through the inspections without stopping and documenting every defect that was encountered. All of that information, all of the defect coding was done back in the office. So we used a nice crawler system with some large diameter tires to get through most of the large diameter pipe. And then in the smaller systems, you can see the transporter there is much smaller. The data, when it's recorded in that format, it just basically takes the top of the pipe and it lays it flat. So at 12 o'clock, it'll take that pipe and lay it flat, and allows us to very quickly look at the inspection results in a very quick format as the pipe is open completely. So what you see there is the inspection form is the output of the actual video work that's done. You can see where the red line is on the PVC pipe. That's the location where the camera is. So if you see something within the pipe that you want to get a closer look at, you just move the line to the areas that you want to look at and quickly identify what defects are in the pipe. PACP scoring was utilized to identify what the actual pipe grade was for each pipe section that was inspected, and we also identified what the rehabilitation recommendations would be once we downloaded all of this video data into our InfoMaster, Univise's InfoMaster sewer module. So very quickly, this is what we got through. Manhole inspections, we did 1,175 manholes, 623 were identified for repair, 86 were priority 1s, 435 priority 2s, and 102 priority 3s. Estimated cost was $1.3 million for the manhole work. Flow testing, we tested 242,000 feet of pipe. We got 35 dye tests, 350 of the defects were on the private, or 350 defects were defective to the private side defects and one catch basin was identified. A lot of these defects, and I could have pointed out on the smoke testing, were in ditches. So what we found is there was a lot of service laterals that were going underneath ditches that had problems with the actual structural integrity of the piping. For nightfall isolations, we ended up doing about 550 nightfall isolations. From the CCTV perspective, we did 633. And then our estimated repair costs, and this was to abate the groundwater infiltration and also fix structural problems that were identified during the inspection work. And the cost on that was $3.3 million. So at this point, I'm going to switch gears and throw it over to Kris, who is responsible for the hydraulic modeling on the project and also for the abatement of the episodes themselves. Kris?
Thanks, Greg. So one of the unique things about this project that we felt sets it apart from others is one of the common frustrations with municipalities in performing studies and investigations and evaluations ends up generating a report that just sits on the shelf and collects dust. So what we did was to create a cradle-to-grave approach to this project, which then took the information that Greg was collecting in the field, and we took that and we were able to turn that into our hydraulic model to evaluate for both dry weather and wet weather conditions. By doing so, we were able to update the city's GIS. We were able to update the hydraulic models that they were provided for accuracy with the inspection data, as well as look for deficiencies within the system. We were able to utilize the flow and rainfall data that Greg collected to insert into the models, and then also the hydraulic limitations for each one. We could identify and expand out within the system to see where that threshold was for needed improvements and increased capacity. So with that, we were able to project out with the 10-year return rainfall events, be able to update the city CIPs and their planning efforts to make sure that they don't need to go back into these systems and do increased capacities and things like that, and reduce and mitigate future SSOs, which was the driver for this project. As I progress into the future slides, you'll see a few case studies that I'm illustrating here that highlight some of the improvements and some of the hydraulic modeling results as we progress through this project. So the first item is Area 1. This was a specific area down Wilcox Road in Indian Rocks. We started doing our evaluating the system as a whole, and trying to identify where those bottlenecks are within the system. So we were able to go through and run the dry weather condition to figure out where under normal operation we would be having potential surcharge, and anywhere that was increase of 50% or more capacity under dry weather conditions was an immediate red flag to us. And we could then go through and identify where we need to focus our wet weather interest in the system for increased capacity. One of the unique ways of handling this project by having done the inspection, CCTV, manhole inspection, smoke testing, all those investigations in the forefront of this project, we can then make sure that we're spending the money wisely for the improvements. Which is critical. Because the last thing you want to do is go through and do rehab based on condition or structural concerns, and then have to go through and rip something out because you replaced it in kind and didn't bother to make sure your capacities were sufficiently met. So that was the intent of doing these models. As we move into the next slide, you can see the hydraulic profiles that we generated for each of these problematic areas to identify what changes and modifications needed to be done, because there were several areas that had sags that Greg identified that we were able to go through and evaluate and see if that was obviously causing problems and surcharges. But we were also able to go through and physically look at these and figure out, maybe the collection system was surcharging, but the manholes weren't, and there was no risk of SSOs. So we were able to divide that out and separate that so that we weren't doing repairs that weren't truly needed under wet weather. So as we progress through the system, you see all these items in red and yellow and orange. So anything yellow, red, or orange in these graphics were areas that we focused our efforts on during wet weather conditions. So as we progress through, you see we also looked for ways to improve system functionality. So there was a bottleneck identified along Wilcox Road where the flow was actually making a 180-degree turn and heading back to the pump station, and there was a significant amount of flow to where those manholes were consistently overflowing. So those were inputs that was provided from the city that we focused on based on their operations input. And with that, we were able to go through and break this into 4 different bottleneck areas just within this one basin to focus our efforts and attention. And when we overlaid in the wet weather conditions, you can see how the map lights up red. These are all focused in these same 3 problem areas that were identified during dry weather and by city operations. But by looking at now the increase in footprint and pipe replacement and rehab based on what's now showing as red, it shows
how much additional effort was needed and the extent of these improvements and capacity improvements were required to be able to accomplish the capacity
we needed during our wet weather events going forward with those 10-year rain events. That being said, some of the bottleneck improvements that we were able to evaluate and be able to run different alternatives in the models to see how they would improve the hydraulics of the system. You can see that we included additional bypasses, which allowed us to remove segments of pipe and abandon in place segments of pipe while maintaining service to the customers, obviously.
But it allowed us to maintain a reasonable diameter of our pipes, allowing for the 2 feet per second flow requirements to prevent sediment buildup, and then also be able to increase the capacity as necessary. So going into some of the other components of these projects, we went through and we compared all the investigation results that Greg gave us with the wet weather results, and we made sure that the system recommendations included his improvement recommendations as well, not just the hydraulics, so that we could be in consideration of every aspect of these improvements, so that it's a comprehensive solution. Looking at some of the dry weather limitations for lift station 28, we took the very similar approach. We had a few instances, for example, on this one slide, you see there's an offset pipe. So we had to go through and evaluate those and model that as well to make sure that that wasn't some of the main causes of the SSOs they were seeing out there. And so we were mindful of all those kind of system improvements in our model as well. And then we went through and we were able to prioritize these repairs. We went through and looked at local community issues. For example, in this one, there's churches and schools and retail stores, things that we had to coordinate with and make sure that we were able to expedite the schedules that matched up with the school system and
communicate these improvement projects with the city customers. But within this one, we identified several problem areas too. And we've highlighted those in blue along the alignments of where those replacements would be based on a hydraulic model insufficiencies. And a lot of the systems had backyard easements and various things we had to work around for these improvements as well, which were close to structures, close to pool cages and pools and other privately owned items that may have encroached into easements that we had to work around for our design. So we incorporated various trenchless investigations and alternatives as well in our approach. That being said, of the 5 problematic areas that we identified within these zones, we progressed through design and construction on most of them. Currently, we're entering in the 4th basin for improvements, and then the final one is actually going to be the largest R&R rehab project that the city's ever undertaken within their collection system. So that was that project should be progressed throughout the rest of this year. We just entered final design on that one, and just as a recap of the design, permitting, and construction approach for the design, we had 7 bottleneck areas identified, and we abbreviated the design process by being able to go for, instead of doing a typical 30, 60, 90, 100% design, do a more comprehensive 30%, and then we would do a 100% design, and we would meet on both of those with the city and incorporate all their ops staff, and we blew through design very quickly. And then from there, we issued our permit sets, and then they issued the 100% design drawings to the pre-approved contractors for construction. So everything went very streamlined. It was very quick and seamless. Since we've started doing these constructive repairs and improvements, it's noteworthy that the city estimates that we've saved the city over $2.6 million in estimated fees that they would have incurred through potential SSOs. So this project has easily paid for itself, and the city identifies this as a benchmark for the community as to how these projects should be approached to be able to stretch your dollar and be able to be proactive to a reactive situation. So with that, I'll open it up to any questions that you may have.